Uh, Welcome, guys, to this warm afternoon. I would just want to start by asking, after our lecture last week, did you guys develop any questions? Please keep in mind that we are studying industrial engineering. We are studying systems engineering in this course. But another lecturer and I had a conversation the other day where we spoke about severely disadvantaged students. So we're talking about child-led households and stuff like that, where students come through NSFAS, and I'm sure there's some of you guys here that have even worse circumstances than that. Where we spoke about, yes, what mentors do our students have, and we are mentors as lecturers. We are mentors for our students, and a mentor is not a thing that is not someone that teaches you everything, but it might be someone that stands next to you in that path that you're walking. And I remember that I was the first person in my family, in the whole family tree that I go back as far as I can remember, the Swanepoel family, my family has been in South Africa. I think I'm the 11th generation. So we've been here for hundreds and hundreds of years, 11 generations, and not one of them graduated. Not one of them got a post-school qualification. I was the first one. And I remember my dad being really supportive. But when I got to varsity, thanks. I don't think that needs applause, because you guys, I mean, you're all there. We're all there. But the thing is, I can remember that my dad was very supportive, and we always had conversations. I have a very supportive dad. So I'm very blessed that I have a dad and that I have a supportive dad at that. But nonetheless, when I got to varsity, I realized that because of his experiences, he was guiding me, but he couldn't tell me what to do. He was the guy that walked next to me while I was on my own path. And I want you guys to see me as your lecturer in that way as well. So I might not understand your circumstances. I might not be going through what you are going through. I might not have seen the same troubles in my life, and I might not reach the heights where you are going to. But I can be the guy that stands next to you with some life experiences of my own. So with that long story, while I was waiting for other students to join us, see our class attendance looks a little bit better now. Sorry. I want to ask you guys, do you have any questions on last week's class? Not, yes, obviously within the technical content, within the course, but also in general about being an industrial engineer out there, or even being a graduate out there, or being a student. You need to pay for your studies, you need to pay for a place to stay, you need to pay for something to eat. And if there's any questions or anything about that, maybe I can give an opportunity now, maybe to raise a question from last week's lecture, or maybe just open a conversation or two. So if you guys would like to raise your hand now, before we start with the lecture, and then I can just touch base on what we're going to go through today. Okay, maybe as we go through the lecture, some questions will evolve and develop. And please do remember, guys, that we will be, this is an interactive lecture. I really, really like it if you guys interact. So that means if you stop me halfway through a sentence or something, I really enjoy that. And I also think it provides a very good learning environment, because half of the learning that you guys will be doing in this course will be from me, but the other half will be peer learning that you guys will be learning from yourselves, between you guys. So please just keep that in mind and do chat. I had the first face-to-face meeting in a long time yesterday, and it was quite different, because all of a sudden there's this soft side as well. So after the meeting, we're standing around chatting. Before the meeting, we stood around chatting. And that's something that you don't see in these meetings. There was physical interaction. We could see each other's eyes and facial expressions and stuff. And that's something that's usually missing in these type of interactions. So please do raise your hands and interact. So let's just go back here. So what I did in the meantime was I uploaded the online recording. So you can see it there. So we can launch the unit. So you can see there's online lecture recordings, which should then have a link to the OneDrive. So you can go to the OneDrive. Hopefully you do have access to the OneDrive. I downloaded the lecture recording, but it was very big. It was very, very big. So if I go to my downloads folder, I think this was it. So it's nearly 500 meg. So I'm sure in here in the repository you can scale it, so you can make it smaller, or it adjusts, the streaming adjusts to your bandwidth. But nonetheless, it is there. I couldn't upload the video itself onto MyTutor because it was too big. So it is there nonetheless. Sorry, this little thing makes it difficult for me. Anyway, let's just go back to our content. So that has been uploaded. It is there. Today's one will also be uploaded. If you want to go to the slides are there. And I believe that the textbook has been circulated on the group. I know the textbook has been circulated on the group. So I'll also just go on the group and put a little full stop there with a link to that textbook. All right, so that's just some feedback. Last time we ended here, right? So we spoke about what makes a system. Systems are composed of components, attributes, and relationships. There. So we looked at a TED Talks video about a guy that applied the systems approach, the systems engineering approach to economics, which was very interesting for me. And if you want to get an idea of who I am as a person, I watch things like that for fun. So you can imagine how strange I am. But nonetheless, he spoke about components, attributes, and relationships. So the components that he looked at was companies, company A, company B, company C, transnational companies, companies that existed in more than one country. Then he looked at their attributes, and their attributes that he looked at was fiscal value, how big the companies are. So a few years back, I think it was before I started with TUT, I remember a big news story that the first company in human history passed the $1 trillion mark, the $1 trillion value mark, and it was Apple. And soon after that, what's that Chinese guy, the richest guy in China, I can't remember his name, but he has things like Alibaba and that media content. Soon after that, he also passed the $1 trillion mark. So nonetheless, that's the value that the attribute that he was looking at was fiscal value. And then the relationships between the companies, those relationships that he looked at were shareholding and ownership. So this one company has bought shares in another company and it owns 40% or whatever. So those are the relationships that he looked at. So that's where we ended last week, that systems are composed of components, attributes, and relationships. So what I want to do today is I want to show you that, yes, that is systems, and that they use that in the science called complex systems, which is also systems engineering, but it focuses on very big systems, very interlinked complex systems. Whereas in our case, we won't be looking, yes, we will look at a wing of complex systems, but we won't be focusing on complex systems. We'll be focusing on systems as are. And there's a different side to that video didn't look at, that we're going to start looking at. And that's the side that this course is about. And now that is hierarchical building of systems, hierarchical structures of systems. Okay. So to go from there, components, attributes, relationships, we can say that the set of components has properties like the behavior of each component of the set has an effect on the properties and behavior of the set as a whole. We saw that, right? So if birds fly in the air and there's a bird and they're flying and they've got an interrelationship, they're flying as a swarm. If one of those birds deviates, it causes an effect on the whole set, the whole system as a whole. Right? So if I've got a plant and one of my machines is malfunctioning, for instance, one of my machines or one of my work environments is lagging behind, it causes a bottleneck and it causes my entire plant, my entire system's production to be low. if I look at a company as a system and say design and the technical side, but now I'm lagging behind in marketing. Yesterday we spoke about future online courses at TUT, and we spoke about timelines. And with my course, which is the new Master of Engineering Management online course, which is hopefully coming next year or the year after, we've gone through the entire approvals process. So it's gone through the Department of Higher Education approval, it's gone through EXA approval, and it's now with CHE for approval. And that's the final step for us. I've developed the content, so all of the content is there. It can just be uploaded onto MyTutor, so that course is ready to go. But there's a link problem with our system at the university at this point. It hasn't been marketed yet, and it also hasn't been included into our ITS systems. So in order for me, even though my work is done, my work as a lecturer, my work as the academic is done in developing the content of this course. But there's other components of this system that's not yet done. The marketing side's not done. The website side is not done. The prospectus side is not done. The registration side is not done. So it doesn't help me at all that I'm ahead, but all of those other sides are lagging behind. So you can see there that, for instance, if marketing doesn't play their role when they're supposed to play their role, then my entire system is lagging behind, because we can't sell this product without marketing it. If I'm manufacturing a car and there's no marketing, how is my client base going to know that there's a car? All right, so one component of our set or our system influences the whole system. The properties and behavior of each component of the set depends on the properties and behavior of at least one other component in the set. So I am dependent of at least one other part of the set, right? So in a manufacturing industry, even the very first workshop, even the very first task that is done on that part, for instance, is dependent on something else in the system. For instance, that part is dependent on the supply chain that comes before it. I have to have the materials at hand to be able to start my process. So that's also a key component of these, property of these components. And then each possible subset of components has the two properties listed previously. So the components can't be divided into independent subsets, right? So you can't see a component of a system on its own. It doesn't function on its own. It is linked to at least one other component, and it affects, it has an effect on the entire system. All right, so that's literally, we're working as a team, and we can't play individually. Okay, but that last one starts to hint at what I want to talk about today. It uses the word subset of components, or we'll talk about subsystems. So there's both a, let's say, series way of looking at it, but then there's also a hierarchical way of looking at it, right? So we can build our system, but within that system, there's also subsystems. And I'll draw you a picture to show you what I'm on about. And it's hierarchical. It's not parallel, it's hierarchical, okay? So systems that alter material, energy, or information are comprised of structural components, operating components, and flow components. Let me show you a picture of what that means. Yeah, structural components, operating components, and flow components. So I'm going to open my my studies from back in the day. I'm going to open my doctoral document, something that I hope you're not bored to death with. But to give you an idea, so in my doctoral, sorry, this is a long document. In my doctoral thesis, I looked at plants, right? So here's an example of what one of those plants will look like. And I modeled these plants in real time. So this was a cement plant. All right, so what my model started looking like in the end was something like this. So here you can see I did a system analysis. So you can see the machines, and you can see that there is link components as well. They're linking up. And then, so there's structural components, there's operating components, and there's flow components. So the structural components would typically be something like a silo or a physical machine like a motor drive or something. And then the link components will be the outflow of my mill, which is there at number 3, is my inflow to my classifying cyclone. And my classifying cyclone outflow is the inflow into my bag filter. And then all oversized particles then drop to the raw meal silo, and the rest gets feedback, right? So all of those flows, those are the link components. And then you get the operating components, which are the components that actually change the material composition. So for instance, what does this mill do to the physical product that flows through it? It changes its particle size. So there's a physical change. It uses energy to change the particle size of this raw material that comes in there. Okay, so how I did that in this document was, or for my specific simulation, is I broke down, there's what my simulation started looking like at the end. So you can see the link components, and you can see that these components have different attributes. So you can see there's a silo, there's a kiln, there's a convergence, there's another silo, there's a finishing mill, and there's blenders and all types of stuff. So what I did in the end was I combined the structural component. I know it doesn't make sense, right? I combined the structural component with the operating component. So in this case, this is a simulation for a mill. But what I said was, okay, there's product inflows because some mills mix products. There's an energy inflow, and then whatever happens in this mill gets multiplied by a certain factor, and it gets stored for a certain time period. Okay, so let me just go back up. So this might be a better description. There's a process of a change in the physical component, and then there's a time delay. So using this, I can also model then things like silos or buffers in general. Okay, so that's those two components. I combined those two, structural components, operating components, and then there's flow components as well, right? So what we did here was, let me just page down. It was it down more? Sorry guys, this was many years ago, so I can't really remember, but I want you guys to have a look at a certain problem that you can see there's my model. So you can see how the systems engineering comes in. Component, component, component. It's got a certain attribute, and then there's also links between the components. So you can see how system engineering can be applied. There's a specific model that I want to show you guys here. So for instance, here we've got multiple outputs, and it can get distributed from one place to another. So this is how I modeled the link components. So you can now see those flow components then becomes these link components, and these link components also have a capacity. For instance, a conveyor belt there, it can do a certain amount of tons per hour. Okay, so they've also got a capacity. And when you start looking at more complex problems, for instance, I looked at a logistics problem at a mine. This was a platinum mine. So you can start seeing that certain plants, let me just zoom in, certain plants can produce certain components or can work with certain components, and other plants can work with other components. So you can see the blue line and the red line. And then I've got, those are shafts, these are plants. So plants can produce certain components and shafts produce certain components. And then there's the distribution. They used trucks. So they transported the ore from these plants, from these shafts to these plants using trucks. So what we did was we looked at an analysis. So this was my flow analysis that I did on these plants. So this was all binary, so you can choose to which plant you wanted to move it. So from this shaft, there's a single output, but that output can distribute it to multiple different plants. Now it's got a choice. So in order, so this is sort of a queuing problem. So in order to analyze that, this was what the output of the model looked like. So you can see from this shaft, it's transported that amount of ore to that plant in the certain time period. So this is what those flow components do. So here we modeled it and we gave this to the mine, and they said, okay, they're going to transport that amount of ore from that shaft to that plant. And by doing that, by optimizing that, you can see here's the optimized solution. We were able to save them 0.1%, which doesn't sound like a lot, but that was 17 million rand in that month. Okay, so you can see the value in looking or analyzing these systems. So those are the three components used in systems that alter material, energy, or information. Okay, so information being computer networks or that type of stuff. You can also see that there's structural, operating, and flow components. Okay, so your buses, I don't know how much you guys know about computers, hopefully more than I do, but you've got operating components, structural components, and flow components. So structural components will be things like your RAM module that stores, your hard drive that stores, the physical chassis onto which everything is bolted. And then there's operating components. Operating components alter something, so that will be things like your processors or your GPUs. And then you've got flow components, which is generally your bus. Yeah, so that's the connection between your hard drive and your motherboard. So that would be a SATA, serial ATA connection, or or that type of connections. All right, so that's also for altering information. For the definition of a system to be complete, its position must be considered in the hierarchy of systems. So here we're starting to talk about hierarchy of systems. So let me start. Maybe I should just finish these two slides and then I'll draw you a picture of what that means. If two hierarchical levels are involved in a given system, the lower level is conveniently called the subsystem, right? So you've got a big system, and then the hierarchical level below that is a subsystem. And you can even go further to say that the subsystem also has subsystems. So let me draw you a picture of what that means. Okay, so I'm just going to draw a new presentation. Let's just make it blank. So I've got a system. So there's component 1. Let's make a simple system. Component 2. Let's do this so that it looks nice. Component 1, component 2, component 3. So I'm going to label it. Edit text. Say component 1. Insert text. Component 2. And this is component 3. Okay, so those are my components. They've got certain attributes. So this might be a mill, a silo, and another mill, or a mill, a silo, and a kiln, or these can be the different stations in your production line. They are linked. Obviously, there's a flow component in between. This flow component has a certain capacity, right? We spoke about what that capacity might be. So let me just link these up. Now, what I said was subcomponents on parallel. So this system could have a parallel line that runs next to it. So from component 1, it can go to component 2 and component 3, and then they can converge into component 4. So it's not just a single line, it can be parallel as well. I hear someone is unmuted. You guys have a question? It might just be a type error. All right, so let's just carry on with this drawing. So it can be parallel as well. So we can say, okay, here's a parallel component, component 4. And it is also linked.
Hello? Huh? Sup?
Guys, could you please mute? It's a little bit of a distraction, I believe, for the other students as well. Nonetheless, So you're starting to get an idea of what a system can look like. We'll use this type of setups when we start calculating all types of stuff, but we're still busy with the introduction. Okay, so there's my system. So it can be parallel components, can be series components, whatever the case may be. So what does a subsystem mean? Subsystem means in this component, if I were to draw it. So we're looking at component 4. That component, inside of it, it can have different subcomponents, 4.1, 4.2, 4.3. Right? So inside this system, is a subsystem. Let me just draw my picture nicely. 4.5. Let's make it dashes. Let's just give it a different color. Okay, so inside that component, there's different subcomponents. So if I take that little block and I blow it up and I zoom in on it, if I go and I zoom in on component 4, it looks like this. So there's little subcomponents in that as well. So an example, if we look at a car, for instance, my components might be, my system is the car. What are the different components in that system? I've got a drivetrain, I've got a suspension, I've got ergonomics, all of that stuff. Now, component 4 is my drivetrain. Now I can go and I say, okay, what's components of my drivetrain? So I've got an engine, I've got a clutch, I've got a gearbox, and then I've got a drive shaft, and I've got side shafts, and then I've got wheels. All right. So in my suspension, what do I have? I've got dampers, I've got springs, and then I've got structural links. All right, in my ergonomics, what do I have? I've got a steering wheel, I've got a seat, I've got an air conditioner. All right, so you can see how you can break those down. So now you can even go further and you can take one of those blocks and you can also break that down into subcomponents. So for instance, ergonomics, I've got a steering wheel, I've got a seat, and then I've got air conditioning. Let me take the air conditioning. What do I have? Right, so I've got a power source, and then I've got the air conditioner itself, then I've got control mechanisms, and then I've got a pipe or ducts that transfers this cooled air into the car, cockpit, and so on. So each one of these subcomponents also has a subcomponent. So you can see hierarchical how it works. So if we were to draw a simple, let me just get a different layout here. So if we were to label it, we can say, okay, this is component, but this is component 1. So under component 1, there's a component 1.1. Okay, so numbering here doesn't work well. Let me show it in Word. Let's open a new document. So let's have a numbering list. So I've got component A, component B, and component C. Okay, so these components are all linked and all of that. But if I take component A and I break it down, component A has subsystems. So it can be component AA, component AB, component AC. All right, and then in those components you can also have subcomponents. So you can see how that hierarchical level develops. Does that make sense? So this is what they're talking about when they say hierarchical systems. So these are the type of systems, hierarchical systems, that we'll be looking at and considering in our course. Okay, so we're going to look at all different types of these types of things. So let's go back there. So if two hierarchical levels are involved, in a given system, the lower level is conveniently called the subsystem, right? So this is my system, and this is my first subsystem. And if I break that down as well, that's a subsystem of this subsystem. And so you can carry on breaking it down into subsystems. Let's look at an example. So systems may be classified for convenience to provide insight into their wide range. So you get natural and human-made systems. You get physical and conceptual systems. You get static and dynamic systems. You get closed and open systems. So you get all different types of systems, and you can classify them in different ways to be able to give you insight into what they do. For instance, physical and conceptual systems. You see that a lot in business practice there, physical and conceptual systems. So physical systems might be computers, offices, networks, stock, all that, production components, plants that you have to rent, all of that types. That's physical systems. And then you've got conceptual systems as well. So what are conceptual systems? Those are things like ethos and policy and community projects and things like that. Those are conceptual systems. So conceptual systems might be the process that we follow to submit an order. Everybody knows if you work in this company, first go and talk to that guy before you order something, or first go through this RFQ, this request for quotation process before you accept a quotation. I worked at Water Affairs. There we had a procurement process. And part of the policy for that procurement process was below a certain rand value, below a certain fiscal value, I can just get 3 quotations, and we can choose the cheapest one. But if it's more than that fiscal value, we have to advertise for tender. And if it's more than that one, there's certain characteristics that you must tender for. So there's a certain way in which a RFQ is set up. So those are conceptual systems. So you can see how you can divide these natural systems and human-made systems. Yeah? So for instance, the natural environment, how birds fly, how ants walk, all of that. And then we've got human-made systems, like a city, for instance, is a human-made system. So we can compare human-made systems like transport systems, roads and cars and that type of stuff with how nature does it. How does nature build paths, roads? How does nature transport stuff? So we can compare those systems. So you can see how we can provide insight by classifying these systems. Okay. So then we have general systems theory. The theory is concerned with developing a system framework for describing general relationships in the natural and human world. A hierarchy of levels can lead to systematic approach to systems that has broad applications. So systems theory is all linked to that one word, is systematic. What does the word systematic tells us? It tells us that there's a structure, there's a certain plan, there's steps to follow. There's certain linkages. So it's a well-structured, planned, thought-out map of how to do something or how something is done. So by using these hierarchical levels that we spoke about, we can use that hierarchical level to break down our system in a systematic way so that we can look at their applications. Okay, so that's general systems theory. So the hierarchy was formulated by bolding as follows. So a system of static structural frameworks encompassing the geography and anatomy of the universe. So that's very high level. And then the level of simple dynamic system clockworks encompassing the significant system or segment of chemistry, physics, or engineering science. So we're breaking down those frameworks into clockworks. And then below that, those clockworks, we break down the thermostat or cybernetic systems, level of a cell or self-maintaining structures. All of this stuff is basically just describing what is out there. There's plant level, there's animal level, human level, social organization. These are all examples of general systems there. And then there's the unknowable. So as far as we study, as far as we look, there's still going to be some things that we don't know. Okay, so we can postulate, we can think about it, but we don't know them. So that's things like nuclear physics and stuff, where below atomic level, there's literally nothing that we can see with our eyes. So we postulate. I know a couple of years back, they found the Higgs boson. I don't know if you know about that, but it was a couple of years ago. They found the Higgs boson. So in the 1960s, I think, there was a scientist that thought about maybe there's a particle, a subatomic particle, that gives everything mass, and that gives all matter mass. It weighs something, it gives it mass. And there's a certain subatomic particle that gives this property to all matter. And he postulated the existence of what we call the Higgs boson. He was a Professor Higgs. And the other day, with this Large Hadron Collider that they have in Europe, they proved that he was right. They proved that the Higgs boson does exist. So then there's the unknowable, right, where we can just postulate like Professor Higgs to say, yes, but maybe there's something more. Maybe something works like this. And that's why it also says are not yet available. So Mr. Higgs or Professor Higgs is long gone. He's died already. But the other day, they proved what he postulated with that Large Hadron Collider. They proved that the Higgs boson exists. All right.
Sorry, sir. Does that then mean, for example, we can see the evolution of animals as a hierarchical system? Or because, I don't want, in a sense, some might have gotten stronger, some might have gotten weaker, or that doesn't matter to the system, the more the fact that its evolution has taken place.
Okay, so let's see if I've got your question correct. In the natural environment, there's an evolution. Some animals, some plants, some human beings adapt based on their environment.
Yes.
If we look at that as a system called an ecosystem, so we can say, okay, there is it's a forest type environment, it's a veld type environment, it's a wetlands type environment, it's a water, sea type environment. So it's seawater, salted water, or it's fresh water, or whatever the environment can be. And we can say, okay, this is how these little animals interact in this environment. So what will happen if we increase the temperature in this environment? Then we can postulate to say, okay, us as human beings, what are we doing? We're heating up the earth, global warming. If we carry on heating up the earth by looking at this system, this ecosystem, which is grasslands and the different animals there, we can say, okay, but mammoths, they've got a lot of hair. If the earth gets warmer, they will struggle to survive and they will start dying. Okay, so we can make predictions. We can postulate responses in the evolution of that environment. So yes, I do agree. We can look at holistic systems like natural environments, and we can, by systems engineering, analyzing those environments, look at systems, subsystems, and then components, and how they link to each other to postulate a future for a certain input. So yes, I do agree there. For instance, what did we look at? We looked at the system and then the subcomponents. Our system is a natural environment. It consists of water, plant life, and animal life. Those are our components in our system. And one of these components is a mammoth, right? So we can take the mammoth and analyze the mammoth in its subsystems. What are its subsystems? It's got a trunk, so it's got a respiratory system, it's got an endocrine system, and then it's got a skin and hair. I don't know what you call that system, but because of that system's malfunction with the natural environment that's heating up, that system's going to fail, and eventually that system is going to become obsolete. The mammoth is going to die out, and the environment's going to adjust, or lions will become bigger and antelope will become smaller, or whatever the case may be. So I don't know if I answered your question or if I even understood your question, but does that give you some clarity on how we can use systems engineering?
Yes, so it's more focused not necessarily on the specific species, but more on the habitat, and then the species is more seen as the components of the so-called environment.
Yeah, remember, this is systems engineering, eh? So us as engineer, what's our natural response? We climb in and we break down in detail. We climb in and we break down in detail, eh, to be able to understand something. That's our natural response. So what I'm aiming to do with systems engineering, or teaching you guys systems engineering, is to tell you, listen, wait, don't break it down into detail. Look at the bigger picture. All right. So we can look at the woolly mammoth and we can say, yes, but it died out. But if you look at the woolly mammoth and you don't consider in what environment it lived, with what other animals it interacted, and how it interacted with those animals, then you have to look at the problem a little bit differently. So now we can look at environmental factors influencing this subcomponent by using systems theory. But if we look at the woolly mammoth as sort, we might not know why it died out, for instance. So in some cases, it's better to use the systems engineering approach, where you take a step back and you look at the linkages to other components. In a simple way, like we saw with that TED Talks, you make your analysis as simple as possible, but the system that you're analyzing as sort is complex. So yes, I do agree. That is a place where system engineering definitely comes in. Guys, I want to end with these two slides. Yeah, let's finish this slideshow, and then we're going to have a few more questions. So all in all, if we get to the definition of systems engineering, what is it? It's an interdisciplinary approach and means to enable the realization of successful systems. Interdisciplinary. So what are we talking about? We're talking about teams, né? So if you're looking at an engineering team that applies systems engineering, it will usually be interdisciplinary. You'll have a civil engineer, you'll have an electrical engineer, you'll have a mechanical engineer, you'll have an industrial engineer, and they're all sitting around a table in an interdisciplinary approach, and they will then be able to analyze the system successfully. So from my experience, if I go and I build a dam, but I'm an industrial engineer, now I want to build a dam, is that system going to be successful? Definitely not, because I will have to have a structural engineer, civil engineer. I will have to have a mechanical engineer to look at the pipe works. I will have to have a electrical engineer for the motor drives, electrical systems, sensors, all that type of stuff. So it is an interdisciplinary approach. Interdisciplinary is also not just in the engineering disciplines. Interdisciplinary could be in your company. So you might have a technical director, and then you have a marketing director, or a PR, personal relations director. Then you'll have a financial director, and you'll have an operating officer, and all of those are different disciplines. But in order for your system, your company to work well, these components have to link up, and then in that way realize a successful system. Going on with the definition, an interdisciplinary collaborative approach to derive, evolve, there's your word, Mr. Gresser, evolve, and verify a life cycle balance system solution which satisfy customer expectation and meets public acceptability. So in chapter 2, we're going to start looking at life cycle. So now we simply looked at the components and the hierarchy of components. But when we look at the entire system in this course, we have to consider the life cycle. For instance, if I produce a cell phone, and Apple has done that, I've got an Apple cell phone. Sorry, it's an iPhone. It's here on the table next to me, so that's why this example came to mind. Yes, they designed the product for client satisfaction. They started producing and marketing the product. They started distributing the product. They've got after-sales service, but they also have to look at disposal. So these days you can actually go and sell your old used cell phone back to Apple, and they've got a whole disposal system worked out. So they can take that phone and they can extract useful materials out of it, and they've got certain reuse, rework, recycle types of networks involved. So that's what the life cycle is about. It's over time, at what stage, what this system will do. Okay, so in chapter 2, so we'll start looking at this. So it's not just interdisciplinary design or interdisciplinary operation. We also have to look at the life cycle of that side. So that's in the systems approach as well, life cycle. So basically, systems engineering is good engineering with special areas of emphasis. So that's what you said, Mr. Gresse. Yes, systems engineering is good engineering. It's applicable, you can use it, but in special areas when focusing and analyzing certain stuff. So some of these areas of emphasis are places where you need a top-down approach, places where you need a life cycle approach, where you're orientated towards the life cycle. A better and more complete effort is required regarding the initial definition of system requirements. So if you use the systems engineering approach, you have to start with a good definition of requirements. Usually that definition of requirements you get from your market or the person that's going to use the system or interact with the system. And then also finally, an interdisciplinary or team approach also helps you successfully apply this technique. Right, guys, so that's the end of chapter 1. It seems as though we went through it very quickly. I'm actually quite surprised. But nonetheless, guys, let's maybe open for about 5 to 10 minutes of questions, and then we'll close off today's lecture. So you guys can raise your hands. For instance, if you've got broad questions, like Mr. Gresse now asked, remember, systems engineering is very broad in application. You can use it to analyze many different things, though we will be focusing on certain things in this course. As you saw with that TED Talks video last week, you can apply it to just about anything. Guys, any questions or comments maybe? Comments for improvement? Kaseya, I don't know if it's a Mr. or Mrs.
Mr.
Mr. Kaseya, yes, how can I help you?
Afternoon, sir. My question is based on more of like, when it coming to the testing of this module, is it more of a practical side of thing, or are you more of a theoretical type of person?
You guys aren't worried about getting the information. You're only worried about the assessment. Even before we started our first lecture last week, you're just worried about the tests instead of enjoying the ride.
I wasn't in the, okay, excuse me about that. I wasn't in the class last week.
No, it's fine. No, I'm just joking. Let's have a look. If we look at our module, so if we go here to the study guide and we open the study guide and we page down to the contents that we'll be covering. So you'll see here that the contents includes some theoretical components and some practical or calculations and stuff. So if we look at Introduction to System Science and Engineering, and bringing systems into being, and conceptual system design. So here you can see it is very, very theory. It's a lot of theory. So our first test will be theory. So here, conceptual system design, the design part already tells you, listen, this is becoming more applied. And then preliminary system design, that's also more applied. So there it will start becoming more practical. And down here, it's economic evaluations, design of reliability, maintainability. So those are calculations. So that's all application. So if we page down to our, where's that? assessment part of it. Here's the assessment part. So you can see here assignment 1, e-test, so that will be theory. Assignment or assessment 2 is a written test. So why would I mark 60 scripts if I could have the computer mark them for me? There's a specific reason, because there's application involved, né? So there you'll see that's application. And then the assignment is pure application. So that's only application. And then in our fourth assessment, there's another e-test, which will be focused on theory, and then written test, which will be a certain extent of application. And then the assignment, again, is pure application. Because, yes, I can check plagiarism, but I can't stop you guys from talking to each other about assignment. And will it be theory if you talk to your buddy about it? And I'm assessing you as an individual. No, it won't be. So that will be pure interpretation and application. Whereas the written test, at least I can stop you guys from talking to each other during the test. But why would I mark a test if I can have the computer mark it for me? It's because there's a certain extent of application. So can you see how those things fit together? Does that make sense? Mr. Kaseya?
Yes, yes. Thank you very much, sir.
Excellent. Thanks, man. Kelebeni. Sorry, I'm terrible with pronunciation. I can't even pronounce my own name most often.
So I have a question.
Yes. Who am I talking to? Mr. Thomas. Sorry, I'm
Yes.
just here at the side who asked first. Okay, so let's start with you, Mr. Thomas. Yeah.
So you said the e-test, the computer marks us, or what? I didn't hear clearly.
Yeah. So what an e-test looks like. Let me show you an example. And yeah, you don't have to be stressed because it won't look like this. I'll open another. Oh, I'm too close now. Let me open another one, an old one. Let me show you what it will look like. Where's my production technology? There it is. Okay, so if we go in there, we go to quizzes, we go to e-test, and then let's look at a. Oh, I'm as student. Okay, let's just go as lecturer. Production technology, quizzes. Let's preview. So this is what your test will look like. Okay, start quiz. Okay, so there's my question. Where does the customer fit into the manufacturing enterprise? Then I have to answer. Okay, let's say the customer does not feature in the enterprise after-sales server. The customer is central. Okay. Why are virtual enterprises necessary for modern business model? They are instantaneously responsive. The whole world is using technology. Reduce cost of design. It makes the design process easier. Okay, because it's instantaneously responsive. And so you answer your questions and then you submit. Okay, so when you submit, the computer already says you have 12 unanswered questions. I said, okay, I don't care. And then it has already marked you. So your quiz has been submitted. You've got 13%. So can you see how your marks are marked by the computer?
No, okay, now so I get it now.
Okay, cool. So some of your tests will look like that. Where was I now? Just exit here. Let's go back to student view. And then let's just go to our block. Systems Engineering 2022. All right, so we're back there. All right, let's look at next question. Kelebeni. Maybe you can pronounce. Maybe you can pronounce it for me so that you can teach me.
Yes. So yes, it's in Kelebeni.
Okay. You've
Afternoon.
got.
Sorry, sir.
Yes. Sorry, you're breaking up a little bit. Good afternoon. You've got a question for me. How can I help?
My question is about the class. Actually, it's about the system. Do you think there's a case in a system whereby the components don't have relationship or attributes, but the operation still function right?
Could you maybe repeat that question? I didn't quite get it.
Or do you think there is a case in a system whereby components don't have relationship or don't share relationship or attributes, but the operation still function right?
Okay, I think there's two sides to your question. The first one is, can a single component operate independently from a system? With other words, it's still operating, but it's not linked to the system. The first question I would ask when that happens, when, for instance, this happens, right? So this component is not linked to that system. The first question that I have is that if that component is not linked to that system, does it add value? And if it doesn't add value, what have you learned in lean design? If it doesn't add value, why have it? So then we should remove it. So what I'm trying to say is, if this component contributes to this system, it will be linked to something. All right. I don't think there's a case where a component operates independently from the rest and still contributes to the function. Okay. And in that case, what do we want to do? Lean design, we want to remove it. Okay. So yes, I believe it is possible for a component to operate independently from the different components. But my first worry would then be, am I analyzing it correctly? Maybe there's a link that I'm not aware of, that I haven't looked at, firstly. And then secondly, if I am correct by stating that this component is independent, I have to ask, does it add functional value to the system? And if it doesn't add functional value to the system, maybe that's the first place where I have to start to make a more lean system. Does that answer your question?
Or so say what you're saying is that it depends on whether the components the component it add value on the system, right? Okay.
If it's a functional contributing component. So for instance, if I've got personnel, now I'm looking at a system of my employees at my company, and one of these employees function totally independently. They don't influence any other employees. They're not linked to any other employees. My first question is, if they're not linked to any other employees, do they add value? Do they add value to my system? If they don't, what does that tell me? Either use that person properly or cut that position. Okay? That's the first thing. Do they add value? The second thing is, if it is it really operating independently? Is that guy not linked to any other people in any way? So with other words, when I look at this one person, yes, he might not be attending the meetings. He might not be an invitee to the meetings. He might not be on the technical team. He might not be on the marketing team. He might not be on the financial team. He's totally independent, but he's still sitting in an office. And that office is budgeted for in the finance side, right? He's still using a computer, and that computer is maintained by my IT component. So the question is, if there is a component that's operating independently, have I really analyzed the system correctly? And if I have analyzed the system correctly, is it adding value? If it doesn't add value, lean theory says cut it. Okay? If it doesn't add value, cut it or use it better. Make it valuable. So I think from a systems point of view, that's what I would look like. What it would look like. All right, Mr. Chiluane.
Good day, sir.
Are you well?
Yes, I'm well, sir.
Excellent.
Yes, actually for me, I need clarification in terms of attribute. Just maybe to put it in a very layman's term. Like for instance, if you say the system consists of maybe component and attributes as well as relationship. Yeah. Maybe if we can give one example of the system, then explain how will we link the attribute towards that component. I don't know if my question is clear, because sometimes I get a mix up, especially in terms of explaining attributes.
Yeah. Yeah, okay. Now I get your question. You're absolutely right in asking that. Last week, I showed a video where I tried to explain that, but I know that it wasn't necessarily industrial engineering concept. So let's look at an industrial engineering concept. Okay, I'm manufacturing a car. So this is my workshop. There's my stations. Let's make it simple. There's my stations. That's station 1. Let's say that is welding. That might be finishing, or let's say assembly. No, let's maybe first say welding, paint shop, and then this might be assembly. Okay, so there's my different workstations. So from the welding shop, it goes to the paint shop. From the paint shop, it goes to assembly. Okay, so those are the links. These are the components: welding, paint shop, assembly. You're asking about attributes. Okay, let's look at these attributes. Let me just go here. Human clip art. Sorry, I just want to copy image. Personnel. How many people do I need? Right, so welding station has 1, 2, 3 people. That's an attribute. Okay. So welding station's got 3. Paint shop maybe only has 1 because it's automated. And then assembly maybe has 4 employees, 4 operators. That's an attribute. Okay. Then if we look at maybe energy demand, so we've got a central power bus running here. There, let's just make it dark blue. Let's make it a little bit thicker so that we can see it. Maybe let's make it yellow. It's power. Okay? And there's a certain power supply to these 3 stations. Yeah. So the power consumption of these stations, that's also an attribute. What's the one? Let me just see. Electricity clip art. Let's just copy that. Copy image. Why isn't it working? My computer. There we go. It's slow now. Okay. Anyway. Sorry guys, now I'm trying to draw a picture and now it's taking me a long time. So this could be electrical demand. Okay. You as industrial engineers, what's the one thing that you do most often? Line balancing. Okay. What is a attribute that you look at in line balancing? It's time. When you do line balancing, what's an important attribute that you look at? Is time. How long it takes through the welding shop, how long it takes through the paint shop, how long it takes through assembly. So that's another attribute. Does that make sense? Is it?
Yes.
Is it starting to fit in?
Yes, and now it comes together. Because sometimes, like for instance, because as maybe the word attribute is so broad, sometimes if you must associate it with example, practical example in terms of maybe answering something, you find that you are missing the point somewhere. So that's why I wanted, at least maybe if you can put it in a very basic and simple way, maybe I'll be able to get it more faster. Thanks.
Yeah. No, you're right. You're absolutely right. Yeah, so it depends on what you're looking at in a system there. What do most CEOs look at? Cost. Né? So all of these things that I'm showing you now represents a certain amount of cost. So what does this welding shop cost me? What does this paint shop cost me? What does this assembly shop cost me? So there are different attributes, and it depends on what you're looking at. If I'm the operating manager, what are the expenses that I pay for? I pay for electricity. So maybe my systems analysis on these 3 stations of mine might focus on power consumption. Maybe I'm an HR manager, and my system analysis focuses on personnel. So it depends on what your focus is on. But you're right, and thanks for that, Mr. Trelawney. Remember, guys, you ask a question, and you're sitting there at home behind your computer, and you're scared to ask a question because just now you're going to be embarrassed in front of everyone, and everyone's going to laugh at you because this is a stupid question. It's not. This was a very valuable question, because I can promise you, Mr. Chiluane, there's at least 10 other people that was thinking exactly the same thing as you. It wasn't a problem with the question. It's a problem with how I explained it. And because you asked that question, I was able to adjust to explaining it to you. So thank you very much for that question. I think it was really, really valuable. Guys, any other questions? Because then I think we should finish off. Okay, you're happy. Guys, we have a recording, so if you're stuck with something, or you didn't catch something, or you entered late, or your computer, your data was finished and you left early or whatever, remember the recording is there, so you're welcome to go back to it. And in our next lecture, you're welcome to come back and ask questions about the previous lecture. Guys, this is an interactive class. That's what classes are all about. Otherwise, you could have just gone and read the textbook. So we are here to learn and help each other. So thank you very much for your attendance, guys. I really liked the way that you interact. It makes sitting at home alone much better for me as well. So thank you very much. I'll then see you guys on Thursday. On Thursday, we'll still be on chapter 1. This is our 2nd week, so we'll still be on chapter 1 on Thursday, and then we'll finalize chapter 1. All right. Thank you so much, guys. Have a great day, and I'll see you guys on Thursday.
Thank you, sir.
Thank you, sir.